Hey, welcome everybody. So thanks for joining us again in this fifth chapter of Herbert's course on environmental fluid mechanics. As always, we're very happy to hear about Herbert's experiences and how he can always teach us something interesting about Navier-Stokes equations. So Herbert, if you could please start now.
Okay. Well, good morning or afternoon or evening or whatever it is for all of you now. Morning for me. I'm not feeling very well today, so I hope I'll do the best I can. Well, I will do the best I can. We'll see how that goes. I can't remember exactly where I ended last time, so I'll start at the beginning of this chapter talking about climate, and I'll go a little quickly at the beginning because I'm sure that's been seen before, and tell you something about the background science, the current situation, some theory and experiments of what you might do to help things, the alternate sources of energy rather than putting out carbon dioxide into the atmosphere, as you see here in this diagram, and then some take-home messages. And of course, the important thing is always that we don't want to end up with terrible floods as we've been having as the ocean waters are rising, or terrible bushfires or total droughts, as you see in one of the other photographs, which we're also having. The beginning of the story really started with John Tyndall, who was the director of the Royal Institution in the late 1800s, a very, very good physicist and scientist. And the last director actually was a PhD student of mine, Sean Fitzgerald. But Tyndall wondered once if he could evaluate, just for fun, the mean temperature of the Earth, because he knew the solar radiation, and he knew that the Earth would surface would take some of that up and warm it up and put it back again. And he thought that would be fun to do. And he made a calculation and got about minus 15 degrees centigrade. And he knew that was wrong. He perplexed for a while, and then he thought, because he was a Victorian, he knew about greenhouses, glass houses that take in solar radiation, that then are able to keep that solar radiation in because it's a different wavelength that's reflected from the ground, and warm the greenhouses. So he thought, well, maybe the Earth's atmosphere acts in the same way. And he thought, well, it's mainly made up of oxygen and nitrogen, so let me calculate the effective trapping coefficients for oxygen and nitrogen. And he found that was 0, really ineffectual. And he was very perturbed by this, and he wondered, and he was almost going to give up his experiments, and really very perturbed when he thought about carbon dioxide. And he knew how much carbon dioxide there was in the atmosphere, less than 300 parts per million. And he calculated then plus 15 degrees, which made it much better. So he was the first to really show that carbon dioxide was important. And you can, in a sense, justify that by looking at the temperatures on Venus, which remain around 470 degrees centigrade, though it's roughly the same distance from the sun, so it gets roughly the same solar input. So why it's so different? Well, the reason is that 97% of the atmosphere is carbon dioxide. So that acts as a trap and makes the temperature on Venus much, much higher than it is on Earth. And we wouldn't like that to happen on Earth. We wouldn't like it to be 470 degrees centigrade, but we're not yet at 97%. Actually, the first person to discover this was a woman called Eunice Newton Foote, and she did her experiments about 5 years before Tyndall, but she wasn't allowed, because she was a woman, to talk about it. It was left for a man to talk in her place. Really quite terrible. Now, there's a lot that goes on in the Earth, there's no doubt, and we'll talk about some of these things, and they all play a role, and especially the ice, which you see here has been melting in both the Arctic and the Antarctic, and I'll show you some data on that. And that's really a great problem because it puts water into the ocean and is flooding places, and that's a problem. But there are lots of procedures going on here, and we'll talk about some of them. This is now the carbon dioxide content at Hawaii. It's now 421 parts per million. You see, even as little as 1960, so that was only 60 years ago, it was at about 315 parts per million. There's the jiggles because there are seasonal variations, and as the trees grow and they take carbon dioxide into the leaves, and then as they die, they give it back to the atmosphere. Now, this measurement was really first taken by a man called Dave Keeling, who you see here in the top left, and he came to the Scripps Institute of Oceanography, which is one of the great oceanographic institutes in the United States and in the world, really. And he came as a postdoc to work with a man called Chip Cox. And Keeling wasn't quite sure what he wanted to do, and Cox wasn't quite sure either. And Keeling then mentioned that he was a good sailor and had a sailing vessel, which he was keen on. And so Cox had the good idea of sending him out to Hawaii, which was away from the polluted area of the central United States, and make measurements of carbon dioxide. Nobody had really done that before, systematic routine measurements. And he made those measurements for some 30 or 40 years, and the measurements are now taken over by Rafe Keeling, his son, which I always find nice. It's a father and son business. But as you see, there's a building named after him, Keeling Building, which even has an old carbon dioxide emissions, or it's not emissions, content in the atmosphere planted on the building. This is now the consequence in temperature. This is something like from 1880 out to 2015. And the important thing is the temperature goes up and down. There are warm years and cold years. It's a big, complicated system. But what you can see, there's been a definite increase in the temperature along with the increase in the carbon dioxide. The carbon dioxide doesn't go up and down anywhere near as much. It has the seasonal variations that I showed you before, but otherwise it is quite smooth. But you see there's a definite correlation between the two, and the more carbon dioxide, which is mainly put in by mankind, almost entirely put in by humans, then the carbon dioxide, put in the carbon dioxide by humans, the temperature goes up as well. This is now showing how the energy is that we use is produced mainly by oil, coal, and gas, and that's been increasing enormously also over the time, a factor of 2 or 3, and they all lead to carbon dioxide outputs into the atmosphere. Nuclear and renewable, like solar energy and wind energy and tidal energy, you can see is minimal. Although it's been growing a little bit, it's growing nowhere near as fast as the problematic output of oil, coal, and gas, and it's nowhere near as large. This is now some records taken from a long time ago, some 800,000 years before present. And what we do is we take ice core records, and from the ice cores, we can determine what the temperature and the carbon dioxide content when they formed was. And what you see there, without a doubt, ups and downs and squiggles. But the most important thing, other than, well, I guess there are two important things to see here. First, the temperature and the carbon dioxide concentration are correlated. When the carbon dioxide concentration is high, then the temperature is high, and low, it's low. But the other thing to notice is that the temperature increase, sorry, the temperature decrease going back to a reasonable temperature takes much longer than the temperature increase. The temperature increase is really quite rapid. You see more or less straight lines. And what that says is that it takes much longer to fix the Earth, to bring the temperature down again, than it does to ruin the Earth. So in other words, our putting carbon dioxide now and melting the ice and causing these difficulties are going to take much, much longer to fix up. This is now more or less the same slide, but with the slightly different temperature range. And it shows you how the carbon dioxide concentrations have really gone up since the industrial times, since about 1850, when human beings have been burning coal and oil and all of this to make the carbon dioxide concentration much larger. And the temperature has also been going up. This now shows one purpose of one part of the input, which is the number of cars in millions. You see, in 1900, there were not very many cars. In the US, there are now something like just over 300 million cars. And in the world, there's something like 800 million cars. In the United States, in 1900, it says there were just 8,000. And there was only 144 miles of paved road in all of the United States. So it was mostly horse-drawn carts that were transporting. And as I like showing in America, whoops, whoa, oh, sorry, how do I go back? Oh, that'll be it. Oh, here we go. There were none in California, no paved roads in California at all. Okay, now this is the number of cars in China, which I got especially from 2011 to 2020. I can't quite see on my slide, but I think it just goes to 2020. It's gone from something like 100 million to 300, very close to 300 million. Really an enormous increase in cars in China. This graph, I think I've shown you before, is the temperature anomalies that has caused. This is the December 2010 against the mean value from 1961 to 1990. And you see, especially in the northern parts, the polar regions, there's really been an increase, a considerable increase in temperature. And with temperatures come bushfires and extinction of animals and great difficulties. And that's what we would prefer not to have. This is now the temperature in Great Britain. And I show this because in 2003, the black line are the observations, and the red curves are some calculations with a big computer program that's held in the US Met Office. And in 2003, there was a rather warm spike, and was estimated there was something like 2,000 more deaths due to elder people not being able to take the temperature and die. Now, by the 2040s, only 20 years in advance, if things keep on going like they're going now, that'll be the average temperature. So there'll be a whole series of extra deaths, which is a real problem. And then once we get to the 2060s, it's the minimum temperature, which would really be a problem. This is taken from about 2 or 3 years ago. It was the hottest February ever on record, says the Met Office. And this is outside so-called Trinity College, where there were flowers already booming. And of course, this summer in Britain, at least, was also very much hotter than previously. This is an example in Australia. And this was an extreme heat wave that was had in Australia a few years ago. This was on the hottest day of that time, on a Friday afternoon. And you see there some bits that were 45 degrees, really enormously hot over a huge part of Australia. And even in the southern parts, it was quite cold. This is now slightly out of date, I'm sorry, but it gives you the idea. The amount of Arctic ice that is present in September, it's at its least extent. And this is now showing how over the years 1950 to 2000, it has gone down. And the lowest, at least in this one, is in 2012, but it's gone lower since then. I should update this slide. But the point is that's very important and makes some people not totally understand this, is if you look at various parts of it, you can see here, it looks as though it hasn't changed much at all. It's more or less uniform. In this part, you might even say the average has been increasing. So it's possible, and people do often make that mistake of looking at the record in the wrong way, looking at only a part of the record. It's the total record you need to look at. This is now the melting that's taken place in the Antarctic. There's a lot of melting on the western side in the Ross Sea and the Amundsen Straits. And you see by the red figures how big they are compared to the 5% loss shown on the top right-hand corner. There's been a little bit of ice gain, as you see in the northeast part, but that's really very, very small. The volume change has really been quite considerable. So here are some numbers, and I can't quite see all of them because, yeah, on average, Greenland lost 280 billion tons of ice each year between 2002 and 2016. And the loss in 2013 was 4 times the loss in 2003. And the Arctic ice loss has tripled since 1980. And it's about 220 billion tons each year. And a billion, just let me remind you, is 1,000 million, as it's shown on the slide here. This is the sea level change. Let me just see if I can get rid of this. Oh, that's better. This is the sea level change over the last 20 years or so. And you see it's almost quite uniform that the sea level has been going up something like 5 or 6 centimeters, the mean sea level. and that's going to cause problems, and has already caused problems in a number of places. No, this won't work. Whoops, why won't this work? Now I can't get on to the next slide. Oh, there we go. This is the contributions to that sea level rise. Most is because the atmosphere is getting hotter, and hence the ocean expands because it's getting warmer too. Then there are glaciers and ice caps that are melting and pouring their water into the ocean. And then you see, even though I said there were huge numbers, the Antarctic ice sheet and the Greenland ice sheet produce a relatively small input to the sea level rise. An important input, and one that we should be very conscious about, but it's not the biggest one. This is just a photograph that was shown somewhere of the Houses of Parliament inundated with water. This would not be a pleasant sight to see. There are definite areas, Tokyo, Shanghai, Rotterdam, London, and other cities that are at risk of flooding. One is Bangladesh, where already there have been quite some problems. It's an extremely densely populated city, and the problems will be twofold. One, that the people in Bangladesh will have to leave. It won't come suddenly. It'll come with time, and that'll mean that they'll be transported elsewhere. And that'll mean trouble for the people who take them in, without a doubt, having a suddenly large crowd. Darwin in Australia is also seen temperatures really close to 160 degrees Fahrenheit, enormously high, and it's also becoming difficult for residents, and people in Darwin are wondering if they should leave to other parts of Australia. There are no doubt some advantages. This is a shot of Putin walking along the rice fields some time ago. It was advantageous for Russia. There was more exportable wheat, but there was lots of damage, the climate breakdown, the bushfires that happened in Australia and elsewhere. And I'm sorry, during the pandemic, it hasn't been easy to get data. And so most of my data comes from before the pandemic. This is now a example of what the temperature has been from 1850 to 2000. And as you see, it's gradually rising. And then the IPC estimate of what will happen. First, there's the high estimate, which says the temperature may go another 5 degrees hotter than it is now, which would be quite considerable, to a low suggestion by the IPCC. But even that is another centigrade and a half. And what this doesn't show is that there will be related fires associated with it, related ocean warming and expansion, ice melting, and really a considerable amount of trouble. Well, people often say, save the earth, and this is a demonstration that was held quite recently. And I say, look, that's not the point. I'm sure the earth is quite safe. It's the people on the earth who need to be saved. That's what we're really, the earth has been around for quite some time, and I'm sure it'll be safe. Well, climate emergency, as people have also said, and we need to do something about it. Well, I hope I've told you enough about what the problems are, and I'd now like to tell you a little bit on what we might do. Oh, first, let me show you. This is a typical United Kingdom Parliament setting. The Houses of Parliament are absolutely full. There's only standing room frequently at the back. The Parliament has expanded slightly over the years, and so there isn't enough seats for everyone. And this is what it was like when they were talking about climate. And you see, there was hardly anybody who was really interested. There was a debate on what to do and how to do it. And that's really, I think, part of the problem, that politicians and heads of business are really not concerned. They do say things like, well, we'll go to 0 degrees in something, a zero carbon dioxide output, I'm sorry, in the year 2050. But by 2050, they'll not be here anymore. They'll not be around. So 2050 is too far in the future. We need to do something really now. This is because the problem mainly because fossil fuels supply over 85% of the world's energy demands. We put out something like 37 gigatons per year, and China puts out the most, I'm afraid to say. It puts out 11 gigatons per year. That's 30% of the total. Then comes the USA, then comes India, and the United Kingdom and Australia are really quite a long way down. Of course, there's a difference between the total output and the output per person, because the populations are so different in these countries. So the mean per person is about 5 tons per year. And Australia, I'm afraid to say, as an Australian, leads the pack. More output per person in Australia. China comes down quite a bit here, something like a quarter of Australia, or a third maybe. And India and Nepal has very little. So some countries need to do more than others to reduce this amount. This is actually a slide which I show in England occasionally. This is actually a Chinese slide. I can't remember exactly where I got it from, but it's actually the sewage output in a city in China. And it shows that with time, the number of facilities were increasing. So was the tonnage of output per day. And when I give this talk in general, I often go to somebody in the audience and say, look, this is similar to the carbon dioxide output. And one might say, gee, should you see if you could have less sewage output? Could you possibly just not need the toilet in the mornings? Well, of course, they say no. And the same is here. We have to change the carbon dioxide output so that we're changing our behavior and doing something different. One way of doing this is to inject the carbon dioxide into the earth, which can contain it. And Sleipner, the Norwegian oil company, decided that they would do. Sorry?
Yeah. Hello, sorry, it's because I lost you there.
And sorry, have you said something, Sergio? Or?
Yeah, hello?
Yeah.
Yeah, I think my internet is again not so good, but yeah, I think now it came back to work. So yes, please continue. Sorry for the interruption.
Okay, it's all right now, is it? Okay.
Yeah, it's thanks.
Sleipner decided that instead of burning off the carbon dioxide, it would extract the carbon dioxide by chemical means and then put it down into the earth, into this porous media, the Atzera formation, which is something like 800 to 1,000 meters depth, and has an impermeable cap rock at the top. The carbon dioxide, when released, is rather lighter than the mainly water-contained interstitial fluid, and so it flows up to the top and comes up to the cap rock and then spreads. So that's exactly what they hoped would happen. They knew that when you put carbon dioxide down, the density increases as it's compressed from being a gas, where you see at the surface it's effectively 100 units, and then it comes down, gets compressed quite quickly at first, and then it gets to a critical depth where it becomes a supercritical fluid and really behaves like a fluid. Further depth increases don't change it much. A gas is really more compressible than a fluid, and so you might as well put it at more than 800 meters, but going much further down is not really worthwhile because you don't compress it much, but you do want to compress it somewhat. So this is what actually happened. They found that they put off the injected point at the bottom of the Atzera sand, and it rose, but it then hit a small region across which it spread, but did move through a little bit, leak through, and that made another region that also found some shale layers that stopped the progress, but then eventually the shale layers were overcome, and it went up and up and up until there was really a proper seal at the top. And so I decided to do some work looking at how this would progress. And so we did some theory and some experiments of having some fluid of density rho go into a porous medium, which is slightly larger density, and it'll form a porous medium gravity current, as you see here, and it'll be a axisymmetric spreading, so that the radius at the front, at the nose, I'll denote by Rn of t, and the height of the current will change with radius and with time. And now, you remember when we talked about flows in porous medium, we said that the Darcy's law said that the velocity was proportional to the pressure gradient. And so that says the pressure gradient here will be the height gradient. So the velocity is proportional to that. And then conservation of volume, which says if the height is going to change, then the velocity has to change slightly, leads to this differential equation, this nonlinear, oh, I can do this, can't I? This nonlinear partial differential equation in R and T, where gamma is determined by the properties, the viscosity of the fluid. Sorry, that keeps on getting in the way. The viscosity of the fluid, the porosity of the G prime, the gravity times the difference in relative density, as you see here, and K, the permeability. And as well as that, you have to add an equation of conservation of volume, saying that the total amount taken up, which is 2 pi RH, I seem to have left it 2 pi out, times RH times dr times the volume fraction is the total amount put in times time. Now, this is a nonlinear differential equation, and they're normally very difficult to solve. But what you can do is you can get a similarity form of solution, a solution that really takes in both radius and time together. And you find that out by saying, look, this term, and Sergio, you can see my cursor going over the terms.
Yeah, yes, I
Right.
can see it.
So this term must be of the order of h over t. And this term must be of the order of gamma. These two r's will cancel, h squared over r squared. So h over t has to roughly be equal to gamma h squared over r squared. This term says that r squared h, because there are two r's here, r squared h have to go like qt. And if you put those together, say those two balances have to hold, then you find that there has to be a quantity which we'll call eta, which is an order one quantity, if you like, that looks like this, that the gamma and the q come from here, and rt to the minus a half. So that says before you do anything else, that the radius has to go like time to the half. So the spread of this current is like time to the half, not very surprising given this conservation law, but this also tells you what the coefficients will be, which you get just by balancing these two, not by solving them directly, but by balancing them. The same thing balancing says that this h, which is a function of r and t, must be a function of the similarity variable eta divided by some non-dimensionalizing quantity, and that's the value of eta, the similarity variable at the nose. We know that that will call that the value of eta at the nose. And then you can write down from this and putting it into here, and I'm not doing the algebra on the board here, but it's all in this paper, if you like, shown during. You get a nonlinear differential equation for f, but it's an ordinary differential equation because it's an equation in the variable that goes from 0 to 1 in y, which is the ratio of this similarity variable eta divided by its value at the nose. So the largest eta can get is 1. Sorry, the largest eta over eta at Rn can get is 1. And so this value goes like 1. You saw, sorry. You solve this equation numerically. It's a nonlinear differential equation, but you also can find that a linear solution, in other words, saying that this height is linear, is not at all a bad approximation, at least for not very small y. Very small y depends on where you input the fluid, whether you put it in here or whether you put it in here. But notice that the similarity variable approach doesn't take that into account. It says, look, it's just got to be right here. Okay, well, when you do that, you find this is the non-dimensionalized Rn as a function of time. And you see that this is on logarithmic graph paper, that this straight line is the value that we calculated, that Rn goes like t to the half, and this is the number that we calculated properly with this appropriate coefficient. And these were for a whole series of different g primes over and q. You see the g prime here ranging from 10, 20 to 80, and q, the input ranging over a factor of 2. So that really agrees with it. And it doesn't matter, which is interesting, whether we put the input in at the base here, which are the open symbols, which you see here, or we put it in at the top, which are the closed symbols. What it's saying is, just as I said for the equation, it doesn't play much of a role what goes on initially. It's only this further part that's important, and that's often true of similarity solutions. And it reaches the similarity solution. I've done another calculation on that and published that recently. It gets to within p% in a time that's inversely proportional to p. So it goes down from 1%, 0.1% in a factor of 10. These are now, we asked, could we please get some data from Sleipner? And we managed to get some data of the time in years and the amount of carbon dioxide they thought they'd stored. And at this point, they only had 3 observations. And so we said, well, we believe it goes like time to the half, or the radius squared should go like time. So why don't we plot the radius squared as a function of time? And now we only have these 3 points, and let's go and extrapolate that back to the origin. Well, as you see here, extrapolates right back to the origin, implying that this horizon 2 got fluid straight away. Also, horizon 3, this is the best 3 point, going through these 3 points, and the origin goes to here. There wasn't any until horizon 4, which is higher up and more to the north. So it's not directly in until after about 3 years. So the implication is that there was no carbon dioxide that poured out over until some 3 years into 4th. But it got into 8 after 1 year, if we just plot this down. And I'm sorry, I'm feeling really not very well now. This is now later in the 2000, and if you look at horizon 6, 9, and 5, you see that it goes very well. Here's the radius squared again, and here's our prediction in the rate at which they're putting it in, and you see the prediction works very well. 5 and 6 worked very well for the lower horizon 2, and then it started to decrease. So there must have been a big hole somehow in what was holding it in that just allowed it to escape, and that's been observed. This is the best trial place in Victoria, Australia, just some 20, 30 miles west of Melbourne, the Otway project, which tried putting carbon dioxide, well, successfully did put carbon dioxide, pressurized carbon dioxide in that depth. And this was a book written by Peter Cook, the manager of the project, on storing carbon. And that, in my opinion, is one of the best ways to go. This is the possibility of sequestration in seven different areas in the United States. And what I always find interesting is they estimate it in billions of tons of carbon dioxide. And they give you a high and a low, which differ by quite a lot, as you see. But nevertheless, even when it's 1,196 billion tons, possibly over something like 300, they quote this to 4 significant figures. So this total comes to 4 significant figures. Well, that's really quite a lot, and it implies that we could get rid of our carbon dioxide just in the United States quite easily. These are the current sequestration sites in the world. You see 4 in Australia, quite a few going on in the United States, quite a bit in Europe, starting with the one that I mentioned here, quite a bit in this part of Asia, but a lot of Asia, there's none at all, none in India, not very much in Africa, especially nothing in Southern Africa, and not very much in South America. And I think that's a pity, because they're not getting very much experience. The cost, well, the cost, it varies, of course, quite a bit. There's the first, the cost of capturing the chemistry, and that's a major part of the cost. And then there's the sequestration, and that's about 2% of the GDP. So, you know, it's maybe something of order of 1 year's growth. Well, as I've said, we've got the cost of capture, transport, and storage to add on to that. But those are coming down, and especially capture, we're beginning to understand the chemistry better. Another possibility is to use hydrogen. And I like this because this is Alan Finkel, the Chief Scientific Advisor to the Australian government. And he's a great believer in using hydrogen. And he always writes to me as H2 to H squared, hydrogen to H squared. The other possibilities, alternate energy sources, because we clearly do need energy, is hydrogen gas. Tides, tidal energy has been shown to be useful, but isn't used very much. Biomass energy, wind energy, which is not always reliable. The wind doesn't always blow as you expect it to blow, but there have been around England, which I'm only experienced with, quite a few wind turbines put in. Geothermal power, maybe use of natural gas, biofuels, wave energy. There's enough wave energy that's created for us to be able to use. Hydroelectric energy, storing energy by pumping it up. Nuclear power, it's a really very questionable input, because some people don't like that. And solar power, use of the sun, which is being used more and more, and hopefully will increase our usage of all of these, and things will get better. Well, I think that's the last slide. Oh, this is just the take-home messages, and I really am feeling very bad now. Global warming is almost certainly happening due to human carbon emissions. And as I said right at the beginning, the temperature of the Earth is related to the amount of carbon, and we're putting more and more carbon into the atmosphere, and the temperatures are going up. One way of combating future problems and costs is to store the carbon dioxide in the many available porous medium sequestration sites a kilometre or so beneath the Earth's surface, and then it'll spread just like flow in a porous medium, as I told her. There may be even better solutions that have been found this morning or tomorrow, but I think we'll be in considerable problems if we don't do anything. And my just slide now is to say, act now before it's too late, because we're already seeing big problems. I think that's all, and that'll have to be all. I'll try and take some few questions, Sergio, but that's all I have to say.
Yeah, sure. Thank you, Herbert. Thank you for being so generous with us to give the lecture despite you're not feeling to your fullest. I do have a question though. about this. So you compared your simple model of gravity currents with the Horizon 2 site. And there was one that indeed was growing the way your model predicted, but then suddenly it went down. And then the model no longer was able to predict that. So I was wondering, what do you think is the reason for that? Do you think it's because of you didn't take into account the something like the capacity of the
No,
of that?
I think
Yeah.
it went down because while for the first part, as it was spreading across, it was more or less stopped by the overlying cap rock. It then
Okay.
came to where there was a hole and it leaked out. And it leaked out and leaked out quite badly. It was almost hardly a porous medium, but it was a hole out of which the quasi fluid carbon dioxide could get out.
Okay, I see. There is one question in the chat box.
See that?
Yeah.
Where? How do I get into the chat box? I don't. Whoops. Whoops. That's something different. Whoops. Come on. Where do I get into the chat box? Why can't I see that?
Maybe you need to stop sharing your screen.
Oh, you ask, stop sharing. Yeah. Hi, Prof Herbert Huppert. I'm curious that will the temperature changing influence the average pressure on the Earth? The increasing of temperature decreases the average pressure. Then we treat the Earth as a granular assemblage. Lower pressure will lead to higher inertial number, which means the Earth will hold a high apparent friction and have high possibility to flow or deform. This will lead more natural hazard happening and geology changing. So does the natural hazard happen more frequently compared with before? Boy, what a good and long question, but I'm terribly sorry I don't know the answer. The temperature changing will change the pressure, but I would have thought relatively small. Remember that a 1, 2, 3 degree temperature change on Earth makes a lot of difference to human habitation, but that temperature change on the pressure, because it's in degrees Kelvin, would only make a 1% change. Well, good question. I don't know the answer, I'm afraid.
Right. Okay, very good. Are there any other questions from the audience? Okay, then I think if not, then we can stop here. Again, thank you, Herbert. We hope you feel better.
So do I, sir.
Yeah, and then we will see you on Tuesday. Let's hope that
Right. Okay.
better.
I hope I'll be better then. Okay. All the very best, Sergio. Thank you.
Thanks to you. Bye.
Bye.